Hi, my name is Karina Shah. I'm 15 years old and I'm a space tech enthusiast whose main mission is to make space exploration and inhabitation a reality. In the past few years, there has been a drastic increase in the number of low-cost satellites that are currently orbiting Earth in low Earth orbit, or LEO. And this produces a huge amount of information that must be transmitted to the ground on Earth from the satellites in orbit in a short amount of time. Such a large amount of communication and information exchange between the satellites themselves and with the ground requires high-capacity communications. However, current mainstream satellite communications are based on microwave frequencies that are not sufficient enough to provide the capacity needed for such information to be transferred. This is mainly because these frequency bands are already crowded and heavily regulated, which only increases the time frame of the frequency listening process. Recently, laser communication, which is also known as lasercom, has become the new source for high-capacity data transfer and communication, as it is an unregulated and uncrowded spectrum, with its feasibility being proven by many space missions. However, even though the issue of a new frequency band for communication and information transfer has been solved, information security still remains to be an urgent issue. The amount of critical, valuable, and confidential data and information that must be transferred from satellites to on-ground has exponentially increased. And in order to accomplish this hack-proof and secure communication, quantum communication is required. So, what really is quantum communication? Well, to answer that question, we must first discuss quantum mechanics, starting out with the word quantum. Quantum is the smallest amount of physical unit involved in an interaction. So, quantum mechanics, in short, is a theory in physics that gives a description of a physical property on the atomic and subatomic level. It is the foundation of all quantum physics and essentially physics in general. Quantum communication uses the laws of quantum physics and applies them to protect data. It is closely related to quantum teleportation and is used in information channels to counter eavesdropping via quantum cryptography or quantum key distribution. The conventional methods of key distribution, which is a form of encryption where multiple systems within a network enable additional systems to access the network by generating a unique key to establish a secure connection, come with many weaknesses, including security issues caused by weak random number generators, unregulated attacks, and the requirement of a high-power central processing unit. Quantum key distribution, QKD, uses quantum mechanics for communicating highly classified and critical information. In QKD, there is a constant creation of completely random one-time keys for maximal security requirements. And there are three main aspects to the process of QKD. Number one, certain photons are sent between a sender and a recipient via a quantum channel. And this quantum channel can be free space and it does not need to be secure. Number two, a quantum key generator and an encryption device is essential to this process. The key is created by a random number generator, which is usually based on the phase interference of a laser beam. So the public authenticated channel uses a genuinely secret key between the sender and the receiver. Here, the photons are the secret key. Number three, key distribution here utilizes quantum characteristics of the photons in order to identify eavesdropping or appropriated informations within the network system to ensure secure communication. If someone even tries to eavesdrop into the network, changes in the quantum properties of this channel allows the sender and recipient to detect attack. With new emerging space technologies, QKD can distribute photons for a distance of thousands of kilometers. And this will allow for high-speed data transmission, low-cost photon detection, and more reliable quantum memories. In a two-part experiment that tested quantum communication from air to ground using an airplane and a ground station, the first part was via telecom fiber channels and the second was via free space transmission. In each of these methods, the maximum distance for successful key distribution was dependent on increasing levels of attenuation and noise. In fact, prior to this experiment, all quantum communication was between stationary systems only, with direct line of sight. However, with this experiment, the ability of key exchange from a fast-moving airborne platform was demonstrated as well. Once a stable and efficient quantum channel was secured, the QKD sender and receiver had to be integrated within the existing communication system within the airplane. Using an advanced pointing and tracking system, the stable transmission of QKD signals at the single photon level was guaranteed, and it also significantly improved the performance of future applications of the classical communication link. If any information had been extracted due to eavesdropping on the ATOM channel, it would be quantified and identified by the observed transmission noise or the quantum bit error ratio, which is QBER. The rotations of the sender and receiver in this rotating airborne scenario were recouped successfully and thus achieved a small QBER. The integration of the QKD hardware, which is shown here, into an existing communication system shows the suitability of QKD as an add-on for a variety of radio links. Thus, the implementation of a stable quantum channel at high rotational speeds is a key milestone for the use of QKD in data transfer in satellites and other high-altitude platforms such as planes, which together form the basis for an efficient and nearly unhackable network enabling secure communication on a global scale. In a second experiment, quantum-limited communication was tested from space, and its goal was to ensure the feasibility of using polarization, which is the direction that the electron field of a radio wave oscillates as it propagates through a medium, encoding on the transmitters which were in orbit, as well as using photon counting on the ground. In this experiment, a microsatellite named Socrates, which stands for Space Optical Communications Research Advanced Technology Satellite, with quantum-limited communication in LEO to ground link was used. The optical ground station was at the NICT headquarters in Tokyo, Japan. It was found that polarization encoding, which uses the manipulation of states of polarization in an encryption-decryption process, is a viable option for QKD from space due to its stable propagation through the atmosphere compared to the time-bin encoding that is commonly used in other networks. After both experiments, scientists realized the importance of precision required when working with the long sequence of received signals. The results demonstrated that clock data recovery and timing offset synchronization could be carried out successfully using data extracted directly from the received quantum states. Additionally, the quantum bit error rate, QBER, is also essential for the QKD process. Once a polarization reference frame is established, the QBER can be estimated, and in this experiment, the bit information 0 and 1 was encoded into binary non-orthogonal quantum states. Scientists were provided with techniques and solutions that will ensure efficient implementation of satellite-to-ground laser comm systems and microsatellite QKD systems that will be useful for polarization space laser comm and polarization LiDAR, or light detection and ranging. The benefits of a space-based quantum network are unparalleled. In fact, there are already a number of proposals that have used quantum networks in space segments to overcome a wide range of purely terrestrial networks. Quantum technologies in general will propel more precise sensors, secure communications, and faster data processing. Currently, deep space quantum links introduce a new area of potential research for quantum communication. In fact, future research should focus on and include the same topics of synchronizations of quantum clocks, quantum teleportation, QKD, but they should also dive deeper into long-range deep space communication because who knows? In the near future, humans will be inhabiting Mars, and this will require secure and efficient communication lines all throughout space. The human civilization will undoubtedly become multiplanetary, and we need to be prepared for this. Thank you so much for watching, and I hope you enjoyed.